We propose a general approach to perform adversarial attacks on triangular meshes.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Random Mocks for Adversarial Meshes, published at SIGGRAPH 2022. I'm happy to host the first author of the paper, Amir Belder. Hello and welcome to the podcast. Can you introduce yourself?
Sure. Firstly, thank you for inviting me to talk. Really exciting. And I'm a PhD student at the Computer Graphics and Multimedia Lab at the Technion under the supervision of Professor Ayala. And my interests are computer graphics and deep learning in general.
Awesome. And who are the co-authors of this paper?
I had help from two amazing master students from my lab, Ran Ben Yitzchak and Gal Yefet, who helped me to run some of the experiments and were really of great help. And my supervisor, Professor Ayala, who was with me the entire way.
All right, so let's get to it. So in a TLDR kind of format, 2-3 sentences, what is this paper about?
Well, we perform adversarial attacks on triangular meshes, meaning on their classifiers, which is not trivial because meshes are irregular. So we had to invent a new solution to do that.
All right, so that kind of brings us to the intro. So what exactly is the problem there? So can you kind of zoom out for a minute and talk about adversarial attacks and meshes and how they go together?
Yeah, so adversarial attacks are pretty much known. What you're supposed to do is you're supposed to take an input. It most probably is an image because most works are in images. And then you alter the image in a specific way to make a classifier classify it wrongly. So what I wanted to do was to do the same with mesh classifiers. But that was a bit different because meshes, unlike images, are irregular because they have varying density throughout the entire mesh. I mean, some regions of the mesh are highly detailed and some are not. And each vertex of the mesh might have a different number of edges coming out of it, which makes it difficult to work. And to add something to the difficulty, meshes have many constraints, like they can't have self-intersections. And well, the meshes I worked on were manifold, which is something we had to uphold, although changing the input to cause misclassification, which made the problem a bit more difficult with meshes.
Okay, let's pause for a minute and take a step back. Let's first talk about so adversarial attacks are basically given an input, let's say an image, and you want to solve a classification problem, right? You take the image, you compute the features, you feed that into a classifier, you get the class. Let's say you have an image of a panda, you want the classifier to say that's a panda. Now, an adversarial attacks basically takes that image, changes it a little bit, right? One of the things about it is to do it very little in a way that is not visually perceivable by a human. So make like a small change. So you take the image, you make the small change, you feed that into a classifier, and then it says, oh no, that's a camel now. So that's adversarial attacks on images. Now on meshes, right? So now you have a different structure entirely. You don't have an image, you don't have a grid, you just have a bunch of points in space and the way they are connected in usually triangles, right? So triangle meshes are most common. Now you have this 3D objects. You want to feed that into a classifier and tell you, oh, this is a mesh of a panda. And then what you want to do in the adversarial context is you want to change the mesh a little bit in a way that you feed that into the same classifier and it will say, well, no, that's a camel, even though you change the points a little bit. Okay, super interesting problem. And yeah, can you elaborate a little bit about the challenges? So why are meshes challenging in that context?
Well, the first thing you have to do is to understand how to impose regularity on the meshes themselves. And then, well, with images, when you change one of the pixels, it can be like a local change. But with meshes, each change is very noticeable, because when you change the location of a vertex, you also change the way the edges that reach that vertex look like. And it might be very, very noticeable. And you might cause self-intersections. And that was really difficult, and was one of the most difficult things we had to solve while working on this paper.
Right. So let me recap that as well, right? If in image adversarial attacks, you change a pixel, right? You just change its color. It doesn't affect anything around it. It just changes that pixel. But in meshes, you want to move a point in space, in 3D space. If you move a point, you basically change the way it looks. It changes the geometry, because it takes all of the edges and all of the triangles that touch that point. It takes them with them. It changes the way they look, the way they are positioned in space. And that's a significant challenge, because you can create a whole lot of mess when you do that.
And it's also very different from point clouds. Point clouds don't have connectivity between their points, and point clouds were the closest representation of 3D models that I had to work with, that had previous works on, and that doesn't happen with point clouds. So that was a really big challenge.
So yeah, meshes are more difficult in this context from point cloud, because the connectivity, which is sometimes, usually it's a blessing, this time it creates a bit of a challenge that you have to overcome. But why is this an important problem? So why do we want to do adversarial attacks, or solve or protect it against adversarial attacks for meshes?
Well, the mesh classifiers are used to two big missions. One is industrial, where they use meshes and their classifiers to determine whether or not the things we manufacture are good. But the other one, which is even more important, is for medical purposes. And when you look at medical purposes, then you really want your network to be robust. Like, I wouldn't want to get a medical diagnosis that's wrong because the cell or the mesh looked a bit different from the regular form. So I don't know whether or not people would actually make adversarial attacks on existing meshes, because they aren't really used for security. But what the paper did show us was how unrobust the features of the mesh classifiers are. And mesh classifiers are used for medical purposes. And so you really want your medical classifier to be robust, and you don't want any small movement of one of the vertices to cause misclassification, which can actually cause to loss of human lives and to wrong diagnosis.
If you had to summarize everything into like a few bullet points, so what are the main contributions of this paper?
First, we showed that mesh classifiers are really vulnerable to adversarial attacks, which wasn't known. Secondly, we proposed a general method to cause adversarial attacks, like successful adversarial attacks that don't break the meshes. And thirdly, we shed some light on how different mesh classifiers classify, because each of the mesh classifiers classifies and relies on entirely different features. And while doing this process, we showed what is important, which regions are important to each of the mesh classifiers.
Let's talk a little bit about related work. So which 2-3 papers anybody coming to read your paper should read first?
So one of the things I really think you should read was Goodfellow's paper from 2015, where he actually started the entire adversarial attacks field, because the attack I use is new with meshes, but was previously used in other forms on images, and he really sums up how and why adversarial attacks work. And the other work you have to read is Mesh Walker, which was the way I chose. I used that as a basis to impose regularity on the meshes throughout by performing random walks on the meshes. So if you read these two papers, you can pretty much understand the paper.
Let's dive into the approach. What did you do and how did you do it?
Okay, so firstly, I'll explain that what I tried to do, and well, successfully did, was performing a black box attack, meaning I had no knowledge on which network I was attacking, and I only had access to the input to the network and to the output, meaning the classification it made on the input meshes. This is important because there are different types of adversarial attacks. This is the hardest part of adversarial attacks, because you don't know who you're attacking, which also makes my approach general. And we showed out a few networks, but we'll discuss that in the results. But what we did was we used a proxy network, meaning as I didn't have access to the actual network as I was attacking, I tried to train a proxy network to imitate the features of the victim network that was being attacked. And then after I did that, I could use the gradients of this imitating network, of this proxy network, to understand where exactly in the mesh the network is using in order to perform its classification. And so I knew where I needed to make small changes to make the victim network wrong.
Does the imitating network have the same architecture as the method that you're trying to attack, or is it?
No. So what I used as basis was I used the mesh Walker network, and I changed it. I changed its loss to better perform this task of imitating the features of the other networks.
Okay,
And
wait, before that. So let me just see that I understand it properly, okay? So you have your input, you feed that into a network that you don't know what's going on inside, and you get an output. Now you take a new network that you do know the architecture, you feed the same input into that, and you say, well, I want this network to give me the same output, right?
exactly.
So now, how do you train that?
So what we did was we took the mesh walker architecture, which classifies by performing random walks, meaning we start from a vertex on the mesh and walk on the edges. And by doing so, we got to see the mesh from many point of views, because the random nature of the walks makes sure that we see it from a few points of view. And what we did was, instead of like saying, well, this is a horse, so take your one hot vector that means a horse and classify that. So I looked at the output of the victim I attacked. So if, for instance, I'm attacking a different network, let's call it mesh CNN, and mesh CNN classified a mesh of a horse as 96% a horse and 4% a camel. So what I told my imitating network to classify was, I give you this mesh of a horse, and your target vector is 96% a horse and 4% a camel. And that's how I hope that imitating network will learn features that are the same as the victim who was being attacked.
Mm-hmm. Oh, okay. So you basically pushed those two output vectors from the original network and the imitating network to be as close as possible. What's next then?
Okay, so once I do that, so once I train a network, which I have to say to the adversarial attacks listeners, well, what we did was actually perform a query once of each mesh of the input, which is how we got the 96 and 4% on the horse mesh, for instance. And I do have to say that mesh datasets are small. So like we did only a few hundred queries for the training. And then we trained the network. And once we got good classification, meaning 100% success in our imitating networks targets, so we used an algorithm to really change the meshes themselves. So what we did was we relied on the gradients. As we perform random walks, each step of the walk, or meaning each vertex inside the walk, has a different meaning on the classification. I mean, some regions are more meaningful than others, like the hump of a camel or the tail of a horse. And well, so these regions we assumed like would be really meaningful to the mesh, and because they are what makes each class unique. And so we needed to understand how we can really relate and really know where to change each mesh. We want to change the most meaningful parts, the most meaningful regions in the eyes of the victim network. And one way to do that is to look at the gradient of the loss, because, well, once our input is full of different vertices from the mesh, so the vertices that were most meaningful to the classification would have the highest influence on the loss function. So what we did was to change the vertices in the opposite direction of the loss, meaning on the opposite directions of the gradients of the loss, and we backpropagated these gradients to the vertices themselves and then move them a bit to cause misclassification.
So let me recap this, okay? So you take your input mesh, right? You create multiple random walks, right? You have these kind of paths along the mesh that you walk around. You feed that into your imitation network that you've now trained and knows how to imitate the network that you want to attack. Now you get your output vector, and what you want to know is where do I need to move points in order to fool the classifier now, right? In order to know that, you basically say, well, I do have the output and I compute the loss. And if I have the loss, I can compute the derivatives with respect to the input. And if I know the derivative, that basically means, well, if I move in the opposite direction, that would actually change the output, the prediction, the classification to be something else than what it is now.
Exactly. One thing that might help understand the idea is like that we usually, when we backpropagate, we update the weights and we leave the input as a constant, and we don't look at it when we update the weights during the backpropagation. So what I did was just do the exact opposite. I used the weights as constant because I said, okay, so my imitating network actually learned the weights that are like the victim I'm trying to attack, and I backpropagated to the input itself. And that's how I changed it.
So instead of using the gradients to update the weights, you use the gradients to update the input.
Exactly. One thing I have to say was it was an iterative process. We did it a few times until we got wrong classification by the imitating network. And once the imitating network misclassified the mesh, we tried it on the actual victim to see if it misclassifies as well.
So it's iterative, right? You every time you move the point a little bit, then run it again, move the point a little bit more, run it again. All right, so let's move on to the results section of the paper. So how do you evaluate this?
So we had to evaluate it in two ways. Firstly, I had to check that the actual victim networks actually misclassify. And that was really important because if I didn't cause them to misclassify, then I just changed the input for no reason. And the second thing is that adversarial attacks have to change the input to cause misclassification, but we don't want to change the input too much. Like if I cause the, gorilla to look like a bunch of unrelated triangles, then okay, it will be misclassified, but the person wouldn't deem it as a gorilla either. So I didn't do anything, so I had to check both. So what we did to check whether or not people think our attack meshes look good, we performed the user study where each mesh was seen by about 50 people. And we just showed them the original mesh and the attack mesh, not saying which is which. And we just asked them whether or not they think they belong to the same class, or one of them doesn't look like the original class, and so on and so on. And we actually got pretty good results. And what the other thing we did was to actually check on a few state-of-the-art networks, the current state-of-the-art networks with mesh classification, and we checked how worstly they classify our attacked meshes, and well, they classified worse. So we had a success there.
Right. So I think that the first experiment is really interesting because meshes, right? You can move a point just a little bit and it will completely distort the shape, right? It depends which point you choose, right? So if let's say you take a mesh of a human, if you move the nose just a little bit inwards, it looks weird.
That's true.
And I think that user study is a really good way of saying, well, how do we know if a small change is actually visually and perceptually small?
That's true. And one other thing that made it more difficult was that most mesh classifiers really simplify the input. So when you get a really simplified input, any change is really noticeable. So we really had to make the smallest changes possible to cause misclassification.
Did you have any unexpected findings or something that you ran and you found interesting in the results?
Actually, the differences between the different classifiers were amazing. I expected like one of the state of the art classifiers to be like more vulnerable than the others, and I found out that all of them were really vulnerable, although each of them uses entirely different features that are based on entirely different things. Each of them imposes regularity in a completely different manner, and still, like, and when you look at the classes each of them misclassified on, so you have like pretty much a uniform split. Like each of them had worse on the uniform part of the classes, which was really surprising.
Yeah, I think this is something that a lot of the listeners don't know, right? It seems like the classification problem on 2D images is basically solved now, but actually in the 3D domain on meshes, point clouds and such, it's still very open research. So a lot of these architectures, they do different things to impose regularity, and then they learn very different features from each other. Most of them are not initialized from any pre-trained large scale model and data set because, well, there isn't one in 3D. So that's something that's important to point out. So what are the limitations, or are there any fail cases?
Yeah, so we do have some fail cases. We found out through our user study that when we look at man-made objects with straight lines and a lot of corners, then our user study showed our attacks were more noticeable on those types of objects, which is pretty much, well, when an object has like a symmetry constraint in three different axes, then it's reasonable that once you change even a bit, then you break some of the symmetry. So that was like our biggest limitation. We still got like good enough results, but it was a big limitation.
Right, yeah, I can understand how that happens, right? If you take a cube or a cuboid, right, and you move one of the corners just a little bit, you're really distorting everything, and it's very noticeable.
Yeah, that's true.
Conclusions and future work. How do you see the impact of the paper going forward?
So, what I really hope would now happen is that people would produce mesh classifiers with more robust features that would just be that would be less vulnerable to such attacks. And for future work, one of the things that I thought of was actually try and make this thing work on textured meshes, because when you add texture to a mesh, it's like a completely different field, and it's really an underexplored field.
Oh, really interesting. Yeah. Because if you distort the mesh and you don't compensate for that in the texture, then yeah, that's going to be even more noticeable than before. Yeah,
Yeah.
interesting future direction to chase up. All right. So moving on to my favorite part of the podcast. What did reviewer two say? Please share some of your experience in the review process.
So, firstly, I have to say that when dealing with this type of data, with not only 3D data, but meshes in particular, then I had to choose carefully the conference to which I tried to enlist the paper to submit the paper to, because not so many people know meshes. And thankfully, well, in SIGGRAPH, they knew meshes really well and really helped because, and I can say specifically about one experiment they asked me to do during the battle, which really helped even me to understand. They told me they wanted to see a comparison to random perturbations of the vertices of the meshes, which actually the viewers really wanted to know and to see that my education's perturbations are more meaningful than just random ones. And I did perform that experiment. And once they told me, I was like, oh my God, how did I not think about that before? That's really important and a really like crucial thing to show. So they really help pointing out like experiments they lacked.
Yeah, I think this is the great part of the review process, right? You're sometimes so zoomed in into the paper and what you're doing that you kind of unable to zoom out and see, well, what is the most simple baseline that I could do, right? Like the random perturbations, which is, yeah, now that you're saying it, oh yeah, of course, I should have done that, right? It's obvious, but you're so zoomed in, you just don't see it. But for your first comment, yeah, I think the field has grown so much right now, right? If you submit to someplace that is very diverse, right? Like, I don't know, CVPR, you have 3D people, you have vision people, you have machine learning people, everybody's doing reviews, and you have random walks, and you have adversarial attacks, and you have meshes in the title. You're obviously in the risk of getting a reviewer that's very well established and knowledgeable in adversarial attacks, but knows nothing about 3D, which is a problem, right? Because in order to understand and evaluate this paper and its standing, you kind of have to have someone that has all of these kind of combined, and it's really hard to find those people, especially because the field has grown so much in the past few years. So, yeah, any new PhD candidates that are looking into which conference or venue to send their papers, always think about these things, right? I can understand why SIGGRAPH would be, a very good choice for this type of paper. Yeah, SIGGRAPH is the ultimate 3D venue, so everybody knows meshes there. All right, that's it for this episode of Talking Papers. Thank you very much, Amir, for joining me. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.